Okay, so I think you on, na? It's on. So I think we can start. So the idea is that today, so yesterday I was saying that yesterday will be the last class on the review of prob and stat, but that did not happen. So hopefully today will be the last class on review of prob and stat. Please settle down. Please settle down. I'm hearing a lot of whispers. Okay. So let us continue from where we stopped yesterday. So if you remember yesterday, we started talking about distributions. And before that, we defined what is probability mass function, what is probability density function, how to compute a probability in case there is a continuous random variable, and all of those things we talked about. So can someone remind me, what is the probability mass function? What is the probability mass function that we discussed yesterday? It's a function that satisfies certain properties. And what are the properties? Fx is between 0 to 1 and sum of fx is equal to 1. And this is only for discrete random variables. And what is probability density function? Correct. And that is an important distinction. I will repeat that probability density function can have value greater than 1. Do not make the mistake of thinking that probability density function is a probability. It's not. The area under the curve will be 1, but one magnitude can be greater than 1. Okay, because it's density and not mass. Density does not represent probability, it is mass that represents probability, right? So to quickly recall, yesterday we talked about PMF, and for PMF the function will have two properties: 0 less than equal to fxx less than equal to 1, which means it is a probability, and then summation over x fxx will be equal to 1, and this is only for discrete random variable. Discrete random variable. Similarly, for PDF, we have fxx greater than equal to 0 and integration fxx dx will be equal to 1. So these are the properties that we discussed yesterday. By the way, those who were absent yesterday there was no recording, so you will not get the recording for yesterday. Okay, so keep that in mind. So that's why I'm repeating the important concepts from yesterday. Okay, and then we started talking about some popular probability mass function and some popular probability density function, but we did not really go into depth. I just named 3 and then I stopped because we were short on time. So let us start from that point. So the first example that we discussed was some popular distributions. Okay, and again, this term distribution I am using in a generic sense. I'm also, when I say some popular distribution, I'm also going to give example of PMFs, and I'm obviously going to give example of PDFs. So the first distribution we discussed yesterday was Bernoulli, right? And Bernoulli distribution represents a random variable or a scenario where the outcome can be either success or failure. For example, if I appear for an exam, I can either pass or fail. If I play a game, I can either win or lose. If I toss a coin, I can either get a head or a tail. And all of those are examples of Bernoulli random variable, right? And what is the PMF of Bernoulli random variable? If xx is equal to p to the power x and then 1 minus p to the power 1 minus x, where x will either be 1 or 0. X will either be 1 or 0. X equal to 0 represents failure, x equal to 1 represents success, and accordingly p represents probability of success and 1 minus p represents probability of failure. Simple, right? Now, yesterday I talked about it and I told it, but I did not write it down. So let me write it down. What is the expectation of Bernoulli distribution? Expectation of Bernoulli distribution. Remind me, how do we find expectation? So I can write mu, for example, or I can write expectation, let's say like this. So how do I find summation of x fx? Exactly, summation of x x fx x. Now, what are the potential value? What will this sum be over? The different values of x. What are the different values of x for Bernoulli? 0 and 1. So let's put 0. So it will be 0. And then fxx for 0 is p to the power 0, 1 minus p to the power 1. Anyways, there is a 0, it is getting multiplied by 0, that's useless. Plus 1 p to the power 1, 1 minus p to the power 0, which means p, right? So your expectation for a Bernoulli distribution is p. And this is okay, but this is also a little strange because you are getting probability is equal to expectation. Because p is nothing but probability of success, and you are getting expectation as probability of success. This is not normal. This is a special case that is happening here. It will not happen otherwise. Okay, it will not happen otherwise, and it is happening only in this case. Okay, remember, I am not going to do it, but this choice of 0 and 1 is a choice that has been made by someone, and you are not bound by that choice. You can decide that my success is plus 5 and failure is minus 9.8. That's absolutely fine. You can decide that. What will happen is that the form of the PMF will change. It has to change to satisfy the properties of PMF, and everything else will kind of change along with that. Okay. What will be the second moment in this case? What is the second moment in this case? Second moment is, I'm not asking about variance. Not sigma x square, that is variance. I'm saying summation of x square fx, second moment. So what will be that? 0 square, right? Multiplied by p to the power 0, 1 minus p to the power 1 plus p square, 1 square, which is 1, and then p. So you will again, the second moment in this case, and remember yesterday I told you that second moment we need to be flexible. He was right when he said that answer, that is for variance. So variance is also a form of second moment, but generally if I am going by the ideal definition, second moment is summation of x square fx dx. Okay, but if I go for finding out the variance, we'll get what you just said. We'll get what you just said. Okay, we'll get p into 1 minus p. So that is correct actually, but we are going by the ideal definition for now at least, which is expectation of x square. Okay, and like that you can find third moment, fourth moment, fifth moment, whatever you want. You can find variance, skewness, kurtosis, and all of that you can find out, right? The second distribution that we were talking about yesterday was the binomial distribution. Binomial distribution. Now, what is when will you use binomial distribution? So it remains same. The output is 0 and 1, but you are performing the experiment or trial multiple number of times, and you are interested in number of success. In this case, you are interested in outcome of your trial, whether it is 0 or 1. In binomial distribution, the variable is over number of success. Okay, so for example, I am playing a game with someone. I can play n number of times. How many times will I win? If that is of interest, then it is binomial distribution. If for a given game, whether I will win or lose, that is of interest, then it's Bernoulli distribution. So they are closely connected, but they are not the same. Okay, so keep that in mind. And in this case, my PDF takes the following form: n c x p to the power x q, which is 1 minus p to the power n minus x, where x represents number of success. So x can vary from 0 to n. You can have no success, and you can always succeed, and then you can have anything between that range, right? So that is the binomial distribution. What is the mean of binomial distribution? NP. Okay, I am not going to prove it, but it is NP, and the variance is NPQ. NPQ. Okay, so P into 1 minus P multiplied by N, as you said, right? So I am not proving it, but you should. I showed you one, you should be able to do others. Okay. There is a limiting condition of binomial distribution, which is quite interesting. So suppose this number of n, the number of trials n, tends towards infinite. So I am performing a lot of trials. Okay, and this p, probability of success, is very low. Okay, then if you solve the limiting case in this case, specifically n tends to infinite is actually enough, you will end up with the, anyone knows what distribution it will become? Poisson's distribution. Okay, so Poisson's distribution is a limiting case of binomial distribution. So it will become the Poisson's distribution. So that is another proof you should probably look into. Again, it's not that difficult. It's just a limit problem. Limit tends to infinite will help you get that. So the actual thing is that n is very large, p is very small, but np is finite, because np will become lambda, the parameter of Poisson's distribution. Okay, so this is the actual limiting case in which the binomial distribution becomes Poisson's distribution, and Poisson's distribution is used for a case where you have countably infinite number of trials. So in that case, actually n tends to infinite, so you have countably infinite number of trials, and it is generally used where probability of success is small. So for example, the number of accidents that might have occurred while playing polo. So that is a very common distribution, because you play polo while riding a horse, and you can fall from the horse, and that can be an accident. But that is very rare for polo players. They are trained, but that does happen. And if that happens, that distribution is probably a Poisson's distribution. Okay. Similarly, throwing a dice. What do you think that distribution will be? Are you aware of the distribution? No, that's a limiting case. I said, I will repeat. I am not doing the proof, but I will tell you that if n is very high, so you are performing a large number of trials, and in theory that is infinite, but countably infinite, 0, 1, 2, infinite, and p is very small, that is probability of success is very small, but np, this number, is finite. Under this limiting condition, you can prove that this will go towards the Poisson's distribution. And the example I gave was playing polo. So polo, there have been so many matches in the history, right? But how many accidents have occurred that has resulted in death? Let's say very few. So n is very large, the number of death probability is very low, but that number if you multiply is finite. So that is generally modeled as a, that is one example that can be modeled as a Poisson's distribution. So that is what I meant. Then NP will become infinite, so that will become undefined. So NP has to be defined, right? So you have a NP number, so that NP has to be defined. Otherwise, if mean goes towards infinite, then you are in trouble. So that is the reason. Okay. Okay. Moving ahead, and this we did not discuss yesterday. Throwing a dice. Okay. What do you think the distribution will be? Throwing a dice only once, and I am interested in the outcome, not in number of success or something like that. What do you think that distribution is? Multinovely. What is the PMF? What will be the PMF? The distribution is known as multinovely, but what is the PMF? I am opening this slide because this might give you the answer. So coin tossing was 2 trials. Sorry, 2 outcomes. Dice throwing has 6 outcomes. So it will be probability of 1 multiplied by that you have got 1, probability of 2 multiplied by that you will get a 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6, but then that summation should be equal to 1. So that is a constraint. So it will be multi-Nowli distribution, and this will be equal to basically product of pi to the power xi I. Okay, this is generic form for dice throwing. This I will be from 1 to 6. Okay, but summation over pi should be equal to 1. So there is a constraint where summation over pi is equal to 1. Okay, and also how is the x represented? I told you yesterday. Suppose I get a 2. What will this x look like? 0, 1, 0, 0, 0. So if I get a 2, for example, let's say my outcome is 1 or 2, then x, this implies that my x is equal to 0, 1, 0, 0, 0, and assuming dice throw, so there will be 6 entries, so 1 more. Okay, so this is my x1, this is my x2, and then you can understand what is happening. So now when you substitute into that expression, you will understand that if it is a 2, only probability of 2 will survive, everything else will go to 1, and it is getting a product, so you will get a probability of 2. Okay, so this is what I was talking about yesterday, that for example in this distribution you have to, the random variable is represented using this one-hot encoding kind of stuff from machine learning. Okay, although it came much before, so maybe machine learning copied it from here. Okay, but it's a one-hot encoding. Okay, this is multinovely. You can easily understand that Bernoulli became multinovely, binomial will become multinomial, and you can make the associated changes. I am not doing it, but you can. Okay, so it will be NC, x1, x2, and all those things, right? So you can do that. These were discrete distributions. Even Poisson's is a discrete distribution. Continuous distribution. So let us go to continuous distribution. So if we go to continuous distribution, then the most easiest one, there is the most easiest one in my opinion and the most popular one. The most popular one, all of you know, Gaussian. The most easiest one in my opinion is uniform, because that is the most easy to deal with. There is nothing 1 by b minus a. So one is uniform, b minus a, and this is basically uniform. By the way, when I am writing 1 by b minus a, I should also write, okay, let me delete it. So 1 by b minus a, as I wrote yesterday, when x belongs to a to b and is 0 elsewhere. Okay, this is the uniform distribution, right? And I'm quite sure all of you are aware of this simplest one. Actually, I used it to show yesterday that the probability can, PDF value can be more than 1, right? Yeah. No, it can touch A and B. It will automatically be, okay, in that sense you are saying. Yeah, you can say that. No, at A and B it will not be 0. Why should it be 0? At that point it has 2 values. It is like that. It is still defined at A or B.
Yesterday you discussed that should be 0 at boundary levels.
You are confusing. Yesterday I draw this diagram. When did I say it is 0? This is A, this is B. When did I say it is 0?
Boundary value should be.
No, who said you that?
In the middle it will be, I think it should take one instance.
That's a different point. That is for any point, that need not be boundary. So what is the probability of a given point for a continuous random variable? It is 0 everywhere. It has nothing to do with boundary. So probability is, because that's a continuous variable. For continuous variable, probability that x will take a given value is 0. That value is anywhere. That has nothing to do with boundary. Okay. So yeah, so this is uniform. What is the mean of uniform? Integration of x fx dx. Fx, this 1 by b minus a will come outside, and integration of x ds will become x square by 2. X square will become b square minus a square, which is b plus a by b minus a. B minus a will cancel out. So b plus a by 2 or a plus b by 2. Okay. So the expectation is integration of x fx dx, which is, sorry, x 1 by b minus a dx, and from a to b, because everywhere else the PDF is 0, so that will not hold. This is equal to, as I said, 1 by b minus a, and then you will get x square by 2, a and b. Now if you put it, you will ultimately get a plus b by 2, right? And if I am not wrong, the variance will come out to be b minus a whole square by 12 or something like that. You can derive it. The variance will come something like that. Okay. One more I will discuss, which is the Gaussian distribution. The most important distribution, the most common distribution, and the most widely used distribution. Okay. This is the most widely used distribution. Any idea why Gaussian is the most widely used distribution? Why do you think Gaussian is the most widely used distribution? Now there is no unique answer, by the way. I mean, your answer and my answer can both be correct. All of your answer can be correct. But what do you think?
Most common in nature.
Most common in nature. So if it has to be most common, then you are saying that the world is symmetric, because distribution is symmetric and things vary from minus infinite to plus infinite. They generally there is, or are you assuming? Because if there is, then things are uniform. Symmetric. And if things are symmetric, that means that the first two moments are actually enough. You don't need higher order moments. Because if things are symmetric, that's what you will get in most cases. So that is potentially not the reason. There can be many other reasons for which, but that is probably not the one. Okay. So what do you think? mean is, so you will not be happy with the answer. The first answer is that because you can do many things analytically with Gaussian. Okay, so first thing is that it is most popular because it allows you to do many things analytically without a very strict assumption like uniform, which assumes everything to be same. Okay, uniform also you can do many things. So that is one reason, but there is a better reason, in my opinion. Again, these are all opinion, as I said. So there is something known as the central limit theorem. You have heard that central limit theorem? What does the central limit theorem states? That if you have n number of variables, okay, and this n is very large, and each of the variable is identically distributed and are independent. So it need not be Gaussian, by the way, it can be any distribution, but this x1, x2, x3 are independent variables and they are having the same distribution. That same distribution can be anything, and that's the important part. So central limit theorem states that if you have n variables, where n is quite large and these n variables are IID, identically and independently distributed, then y, which is a summation of this x, x1 2 plus x2 plus x3, will always be following Gaussian distribution. So that means if I make this hypothesis that whatever is happening in the world is because of there is multiple factors affecting those, and if those factors are additive in nature and they are IIDs, then the final distribution will be Gaussian. So this is a very powerful theorem, central limit theorem, and this actually justifies in many cases that why we take the noise to be Gaussian. You will see that the noise is taken to be zero mean Gaussian in many applications. That is well justified because you assume that the noise is coming because of different factors, and those factors are IIDs. What distribution you do not know, but they are IIDs, they are independent factors and they are having same distribution. If this assumption you can take, then the final will be Gaussian. Okay, so in the type slides, I will not go there, but you can check it out when I upload it. There is a MATLAB code which shows this. Whatever I just said, you can use that and play with that. You can increase the number and it will see that it will go to Gaussian. So I take, I think, 1 uniform, 2 uniform and 10 uniform. You will see that by the time I reach 10 uniform distribution, it is Gaussian. Okay. So that is another opinion again. That might not be the reason, and there can be n number of other reasons. Okay. Clear? Why is Gaussian so popular? But I think the most popular reason is, the first one is actually the more used. I mean, you can do things analytically. So that is a very strong reason actually. So Gaussian distribution. 1 by sigma root 2 pi exponential of minus half x minus mu by sigma whole square. Okay, this is the Gaussian distribution with parameters mu and sigma, where mu stands for mean, sigma stands for standard deviation, or sigma squared stands for variance, if you want to. And generally this Gaussian, by the way, is denoted by this form. So this is how we will denote Gaussian: a calligraphic n, then the variable name, and then conditioned on, that means those are the parameters, mu and sigma square. Fire alarm? For uniform, it will be x given a comma b, where a is the lower limit, b is the upper limit. For Bernoulli, it is generally calligraphic BER. By the way, this is also calligraphic. Okay. So Bernoulli BER, binomial BIN, beta B, and all those things. Okay. Beta B and all those things. Okay. As I said, expectation of a Gaussian distribution is mean. So expectation, this is mu, and if you calculate the variance or standard deviation, that will come out to be variance will be sigma square, standard deviation will be sigma. Now for Gaussian distribution, there are many things you cannot do analytically. There are some identities that you can do, but if you do by hand, you might not be able to do it. For example, I don't think you can integrate it from minus infinite to plus infinite by hand. There are some identities that you can use, but by hand you might not be able to do it. Because you know, right, integration is not always possible in an analytical sense. Okay, and that is why there are identities that are used. So one of the identities is, for example, identities, and these are quite popular identities. So integration of exponential minus z square by 2 dz. Can you tell me what will be this equal to? What do you think this will be equal to? This is your clue. What is sigma in this case? What I have written? Sigma is 0. Sorry, sigma is 1. And mu is 0. And you know Gaussian distribution or any distribution for the matter of fact should be normalized. So if this has to be normalized, then this should be equal to, because then if you put it below, you will get a Gaussian distribution with mean 0 and standard deviation 1, which is known as the standard Gaussian distribution, standard normal distribution. So this is one identity. Similarly, the other identity is integration of z exponential of minus z square by 2 dz. This will be equal to, I think from odd function, even function you can tell, but this will be equal to 0, 0, mean is 0. Okay. Okay. And by the way, I am not writing, but this is minus infinite to infinite, minus infinite to infinite. Okay. Now, some other popular distributions are log normal distribution, and you will encounter this in this course. Because, okay. Then you have the Rayleigh distribution, then you have the beta distribution, then you have the gamma distribution, and then one distribution that is quite popular in reliability, at least in time dependent reliability, is the Weibull distribution. And Weibull distribution, there are two types. One is 2 parameter Weibull distribution, one is 3 parameter Weibull distribution. Okay. And then there is the Weibull distribution, and it has two types, 2 parameter, which means it is defined by 2 parameter, and 3 parameter, which means it is defined by 3 parameters. Okay. And there are many others, by the way. I mean, there are many other distributions, and you will encounter some of those in this course, but the one that will encounter the most is the Gaussian distribution. Okay. And we'll see that in many cases things are done after transforming the distribution to Gaussian distribution. Okay. In many cases we will see that. Okay. By the way, whatever distribution I showed, I only showed univariate distribution. That is a variable that is univariate, one value it will give for a sample. But it is not necessary that you will have distributions that are univariate. You might have distributions over vectors. So that will be multivariate distribution. And you might have distributions over fields or functions. So Gaussian process, for example, we will be talking about. So Gaussian process is a distribution over function. So each sample will become a function for Gaussian process. Similarly, for a vector valued distribution or a multivariate distribution, to be more specific, each sample will be a vector. Okay. So for example, and there are courses on multivariate statistics you must have heard of. So for example, multivariate Gaussian. Okay. Gaussian. So this is 2 pi to the power minus k by 2 what is capital sigma? Covariance matrix. Okay. And how does the covariance matrix looks like? The diagonals are variance, not standard deviation, and the other terms are covariance. Okay. So sigma is your covariance matrix, and then exponential of minus half x minus mu transpose, then sigma inverse x minus mu. Okay. So this is the multivariate Gaussian. And what is the dimension of the Gaussian? K. That's why it is minus k by 2, because it is root 2 pi. So that 2 is coming from the root. The negative is coming because it was in the denominator. And k is coming because now it is k dimensional. Okay, previously it was one dimensional, so you are getting 1 square root of 2 pi, 1 by. Okay. So this is a multivariate Gaussian. You can have like that for others also. There is Wizard distribution which is multivariate, and everything can be multivariate. Okay, everything can be multivariate. Okay. For multivariate distribution, and this is where again the independence thing will come into picture. What is the number of parameters that is unknown? What is the number of unknown parameters for multivariate? By the way, so today I am trying last 10 minutes, so try accurately last 10 minutes. Okay. So I am trying to figure out how it will work. Obviously, I will take pen and paper also. So yeah. So yeah, what is the number of parameters that are unknown here? 2. 2k. How? First, let's talk about mu and sigma. There are two big parameters that are unknown. Mu, what is the size of mu? K, because it's a vector. Then there are k unknowns in mu. Sigma, what is the size of sigma? K cross k. What is the number of unknown? The diagonals are unknown, and it's a symmetric, so either lower triangular or upper triangular, right? So it will be k into k plus 1 by 2 plus k, something like that. Okay, you can do the maths, but it will be something like that. Okay, so the number of unknowns is quite high. If k is 100, then 100 and plus, broadly speaking, 100 square. Broadly speaking, it will be less than that, but it is in the order of 2, or right? So it is quite high, and it is high because of the covariance matrix. Everyone agrees? Because that is in square, so it is high because of the covariance matrix. Now, what will happen if I assume that these are independent? What will happen to the covariance matrix? How will it look? If the variables will just be a diagonal, number of unknowns will reduce to k. Total unknown is k plus k. Total will be k plus k. You can clearly see that with independence, even in this kind of problem, the number of unknowns can be reduced drastically, right? So that is basically the advantage of considering things to be independent, if and only if that is possible. I mean, it might not be possible to take things independent, and in that case you have to deal with whatever it is. You don't have an option. But if possible, we will always try to or like to make things independent. Okay. I repeat.
IIT assumption which you mentioned earlier, does that mean that their specific covariance matrix is a diagonal matrix?
No. So in that case, the variables were IID. So the variables were independent. So let's put it this way. Let's say x1 is a multivariate variable, x2 is a multivariate variable. x1 need not have a diagonal, x2 need not have a diagonal, but they are IIDs. Covariance diagonal. So x1 is a vector. So x1 is a multivariate variable. Okay, so let me write it down. This is a good question, so we should clarify it. So we are talking about x1, right? So let's say x1 belongs to K. Okay, so it's a K dimensional. x2 also belongs to K. Okay. So now it is very well possible, or it is very much possible that this K that you see are dependent, but this and this are independent. So in that case, I can say x1 and x2 are independent, and they might be also be identically distributed. But x1 has 10 components, and they are dependent. You get the point what I'm trying to say?
Like we have a multi-feature space,
Hmm.
then I was thinking that each feature is like x1, x2, x3.
That's one option. The other option can be that x1 is itself is a vector, x2 itself is a vector. So in this case, if I combine them and make a common variable x, that you can always do. I think that's what you are. If I make a common variable x, how will the covariance look like? You will have a covariance something like this here, and you will have a covariance something like this here, and this will be 0, this will be 0. That is what you will end up with if I combine this x1 and x2. So you cannot use IID assumption on this. You cannot use IID assumption here, but you can always combine these two are IIDs, assuming same distribution, obviously. No. X separately x1 and x2. So in that case, x1 is a multivariate, x2 is a multivariate.
The values in x1, they are independent.
No. X1 samples are dependent, but x1 and x2 are independent. Very simple example, let me give you. Okay. Suppose, let us talk about a multivariate distribution. Okay. Let us say I am taking the elastic modulus of this pen at 5 different locations. They are dependent? They will be. So, correct? So now these 5 locations, I will get a 5D vector, and that distribution, let's say, is Gaussian. Simplify. So this is a Gaussian, 5-dimensional Gaussian. Okay. Now let us say I am taking elastic modulus of my finger. Again 5 points. Again it will be a 5-dimensional Gaussian. Now this elastic modulus of my finger is independent of the elastic modulus of the pen. But this is 5-dimensional and they are dependent. And here there are 5 points, they are dependent, but these two are independent. So this is my x1, this is my x2. Clear? So generally we think in 1 dimension, but it need not be. Okay. But when I am saying that independence will help, when I was saying here that independence will help, then I was talking about only elastic modulus and if those are independent. In that case, I was saying that. So that is the best case scenario. That I have 100 or 5 plus 5, 10 points, everything is independent. In this case, I have 5 plus 5, but one 5 group is dependent, other 5 group is dependent, but these two groups are independent. Okay. Think about it. If it is not clear, please come to me and we can take more examples. Okay. Okay. Multivariate Gaussian we talked about. And similarly, as I was saying, there will be other multivariate distributions as well, and we will encounter multivariate distribution. So one thing, and I will not discuss it today, but I will just like to mention, that because of this independence thing, we like to work with independent random variables. Okay, and there are strategies using which we can do transformation of random variable. Of random variable. So I can transform any random variable to any other random variable, at least in theory. In practice, it's not so straightforward, but I can, okay, in theory. And this is what we use in many cases to allow us to work with Gaussian and independent Gaussian variables, because I will transform some complex dependent random variables into a Gaussian space where variables are independent, and then the algorithms will be on those. This we will see probably starting next or next to next lecture, so I'm not going to talk about it today, but you can do transformation of random variable, and generally there are many ways. There is this Rosenblatt transformation which we will talk about. Rosenblatt, okay, Rosenblatt transformation, and then there is this NATAP transformation that we can work with. And both of these allows us to transform variables from one to another. But in general, yeah, both of these allows, and both of these are works based on inverse CDF approach. So if you know the CDF, you can invert it, and that will take you to go uniform, and from uniform you can go to, so you can go from any distribution to uniform by using inverse CDF approach, which we'll talk about in details. But in general, it is this is generally a uniform distribution. Okay, so in general this is the thing, but we'll talk about it in detail, so I'm not going to into the details of it now. But the point I want you to remember is that it is possible to transform distributions. You can make a dependent distribution, take it to some other space, and that will become independent. You can, yeah, and you can still keep it dependent, and all those things is possible. Okay, so transformation of distribution is possible in theory. In practice, for many cases, it is not possible. Okay, but in theory, it is possible, and we will be using it extensively in the analytical part of things, which is the first part that will start next lecture, and also in some sampling, in some for subset simulation and all those things we will be using it. Okay, so remember that transformation of distribution is possible. So with that, we are done with the review part. I'll just go to the slide and show you once. So the previous 2-3 lecture slide have been uploaded on the website. The first lecture video has been uploaded. The second lecture is not yet uploaded. Third lecture will not get video. Today will get video. Okay. So these are things which I have not covered, by the way, likelihood and all those things. You can study it, but we will need it probably much later in the course, and at that point I will cover it. So binomial, this is the multinovely. Okay, and then for multinovely, some proofs are there, MLE estimates are there. This is summary of multinovely, multinomial, Bernoulli, binomial. Students T I forgot to mention, but an important distribution nonetheless. It is again a generalization of Gaussian actually. Cauchy's distribution is there. I only talked about some, but these are some other distributions that you should study this on your own, okay? And you can expect problems from here in the first 4 more, without a doubt. Covariance you are aware of, so I kind of skipped, but I talked about multivariate random variable, I talked about. This thing I did not talk about, so let me quickly highlight that you can go from a CDF to a PDF by taking a partial derivative, okay? And you can go from a PDF to a CDF by taking integration from minus infinite to the value at which you want the PDF, okay? Multivariate go. So yeah, this is how the covariance matrix looks like. Yeah, this is correlation matrix. We talked about it. So there is some MATLAB course you can try out for sampling and all those things. Law of large number I did not talk about, that we will need in sampling. I did not intentionally talk about it. I will bring it when we go to sampling, we will not remember. Central limit theorem is what I was talking about. And this is the MATLAB code. You can see uniform 1, 2 and 10. By 10 it is almost a Gaussian. So just play around with these codes, I will say. And this is not relevant right now, but this is a Monte Carlo approach for computing with a value of pi. How you can compute the value of pi using Monte Carlo estimate. So this is corresponds to that. This again relates to sampling. So if you want to be ahead of the curve, do look into it. If not, I will be covering these things in the second part of the course when we go to sampling. So first part is analytical approach. There we will do analytically. Second part is sampling, where these things will come into picture. Third is surrogate based approach, where machine learning, Gaussian process things will come into picture. And then there is a miscellaneous at the end, which is system reliability, time dependent reliability, and so on and so forth. Okay. Any questions? Again, I will repeat that do look into the type slides. Okay, that is very important, and that might help you in getting some common questions in the homework, although unlikely, but might be 1 or 2 questions. Okay. Okay, so if there is no questions, thank you.